Hello everyone. In this video, we're gonna begin our study on exponential functions. Exponential functions. Okay, and we're gonna learn how to take derivatives of exponential functions. So, what is an exponential function? So if you remember from an algebra class, you might remember that an exponential function is equal to some positive real number, a, which is called the base, is raised to a variable exponent, x. Okay, so the variable is your exponent. So f of x equals a to the x. Now, you might remember from a graph of an exponential function that once it gets to the first quadrant, it starts shooting up. Although when x starts to get negative, it starts to flatten out and tend towards zero. So that's the typical graph of the exponential function. But there is one number of the base that is really, really interesting and important to keep in mind when talking about exponential function. That is the number e. So again, this should be a callback to algebra or pre-calculus class, that e is defined as, you can define as a limit as n approaches infinity of the expression 1 plus 1 over n to the nth power. So as n becomes larger and larger and larger, tends towards infinity, increases without bound, the expression in the brackets will tend closer and closer to this special constant e. Okay? And it's a fixed constant, and it's equal to approximately 2.7182818284845, and so on and so forth. E is an irrational number, so it never repeats and it never ends. Okay? So this is a mathematical constant. It will never ever change. This is what e is. And we're going to focus on the derivative of e to the x. The derivative of e to the x. And it's quite surprising, really. So rather than give it to you, let's try to find it on our own using the limit definition. The limit as delta x approaches 0. Hope you remember this. Of f of x plus delta x minus f of x, all that over delta x. So our limit definition, remember when we first started derivative, this was how we would find it. And we're going to apply it to this. We're going to apply it to e to the x. So we're basically trying to find the limit as delta x approaches 0 of e to the x plus delta x minus e to the x, all that over delta x. Now, what you might notice is that e to the x plus delta x equals e to the x times e to the delta x. So what we can do right now, this is just exponent properties, is we can factor out an e to the x, okay, since it's present in both terms of the numerator. So we have e to the x times e to the delta x minus 1 over delta x. And since e to the x is a constant, okay, it's a constant term, we can pull it out and focus on this inner limit. Okay, so this is where we have to focus. Now, if we do direct substitution, and plug in delta x equals 0. So if e to the 0 is 1, minus 1 is 0, divide by 0. So that means there could be a solution, okay? So to find the solution, what you have to realize is there is another way of writing e as a limit. So we know that the limit as n approaches infinity of 1 plus 1 over n to the nth power is e, okay? But what if we make a substitution that n equals 1 over k, where k is also a real number? So what happens as n approaches infinity? As n approaches infinity, if we solve for k equals 1 over n, you see that as n approaches infinity, k approaches 0. So we're basically rewriting this limit. The limit as n approaches infinity, the limit as k approaches 0, the limit as k approaches 0 of, and we just have to make the substitution. 1 plus 1 over k, so that's k, to the 1 over k power is also equal to e. Okay? And now you can kind of see where we're headed. We have a delta x approaches 0 and e to the delta x. Okay? So because it approaches 0, we can make a nice and easy substitution. Okay? And it's perfectly legal. You don't have to, there's no double limits going on here. Because if you remember when we did limit properties, this is completely legal. The limit of a quotient is the limit of the numerator divided by the limit of the denominator. Recall back to our very first couple of lessons. So that is equal to, can't forget this e to the x outside here, that is equal to e to the delta x. So e is equal to this, except we replace k with delta x, since delta x is approaching 0. So we have 1 plus delta x to the 1 over delta x power, that's e, to the delta x power, minus 1 over delta x. Okay, remember, it is perfectly fine. We can substitute this expression since it's all inside the limit. Okay? Now the exponents cancel out, which is what we were waiting for. And the ones also cancel out, because 1 minus 1. Because the exponents cancel out, we can do normal subtraction. The ones cancel out. And now we are left with the limit as delta x approaches 0 of delta x over delta x. That cancels to make 1. So this limit evaluates to e to the x times 1, which equals to e to the x. That's strange. Our function was e to the x. And that brings us to a very, very important rule. We just proved that the derivative of e to the x equals e to the x. And it's the only function that is not the only non-constant function, since f of x equals 0 also has this property, but the only non-constant function that has this property, okay? This property, this magical property that the derivative of the function is itself, is the function, okay? So let's do a couple of examples. So we want to find if f of x is equal to e to the 2x, what is f prime of x? F prime of x is equal to, this is just the chain rule, okay? We take the derivative with respect to the inside function, which is 2x. So if e to the 2x, it's itself. times the derivative of the inner function. That's 2. So we have that over here. So it's 2e to the 2x. So for the exponential function, this is actually one of the easiest derivatives since it's just itself. There is nothing complicated about e to the x since it's literally itself. So why not? Why not we do another one? Why don't we do another one? So let's say we have, let's do a fun one. This is a favorite of mine. Let's say you have the graph of f of x equals e to the negative x squared, which if you don't know is a bell curve because it kind of looks like a bell. Hence the name bell curve. And we're looking at the first quadrant. Now, with this derivative, with the derivative of e to the x, you can solve lots of fun problems like this one. So imagine you had a rectangle, okay? Such that one of the vertices is the origin, and the other is on the graph. The other's on the graph, and you draw a perpendicular line to the axis, so you form a rectangle that way. So this is a rectangle, and if we pick this point, it's also a rectangle. What is the largest possible area they can make using this? And this is a fun one, okay? It's a fun one because it is an optimization problem, okay? And you know those are always pretty fun and pretty hard. So let's see what we can do here. How can we express the area of this rectangle? The area of the rectangle is A equals x, we're going to define this as x, times f of x. Okay, this side is f of x. This is f of x. This is x. So the area is x times f of x, which equals x times e to the negative x squared. Now, switch back to black. We just need to use the product rule. So we have f prime 1 g plus g prime. What is g prime? What is g prime? G prime, we take the derivative of e to the negative x squared, we get negative 2x e to the negative x squared. So we have negative 2x e to the negative x squared times f, our first function, x. And this equals e to the negative x squared minus 2x squared e to the negative x squared. And we want to set this equal to 0, find some critical points. So we can do factor out e to the negative x squared and solve this equation for 0. And what do you get? Well, you get x equals, well, the first factor can never equal 0. The exponential function is always positive. And you can see from this graph, this is always positive as well. So we have to take in the second factor. And we get x equals 1 over the square root of 2. Or root 2 over 2 if you want to rationalize your denominator. So x is 1 over root 2, but wait, you have to verify it. Okay? So if you were to take 1 over root 2, which is approximately 0.707, we're going to check 1 and we're going to check 0. So for 0, you have a positive value. Okay? And for 1, you have a negative value. So it's going from positive to negative. This is indeed a maximum. Okay? So this is a maximum. So we're trying to find the maximum area. So we know that area is a maximum when x equals 1 over root 2. So our total area equals 1 over root 2 times what's e to the negative x squared. So that's e to the negative 1 over root 2 squared, so negative 1/2. Or 1 over root e times 1 over root e, and we see that this is 1 over the square root of 2e. Okay, this is a fun one. Okay, let's do another one. Okay, there's a lot of these you can do. A lot of them. And what we want to do is we want to find, let's do another type of problem. Let's have a graph of x times e to the y plus y times e to the x equals 1. And let's find the tangent line to the graph at the point 0, 1. Now I picked this one. Okay, I'm planning to do this one because it's implicit differentiation. Okay, another technique that you should remember. Okay, so now you see starting to dig up old wounds, dig up old graves. Okay, as you want to remember all of these. So you take the derivative with respect to x on both sides equals 0, derivative of a constant is 0, and we apply the product rule to both sides. So f prime g plus g prime x, remember we put dy dx there because of the variables don't agree, so chain rule, she watched her video to remember that, plus the product rule on this term. So f prime g plus g prime f. All that is equal to 0. And what do we get? What do we get? Well, if we were to isolate the dy dx terms, so you have e to the y plus ye to the x equals negative x e to the y minus e to the x times dy dx. Okay, we're just subtracting them and factoring out dy dx, as you would do with any implicit differentiation problem. And if we divide by this, divide by negative x e to the y minus e to the x over you do this, we get dy dx equals negative y e to the x plus e to the y over x e to the y plus e to the x. We just pulled out a negative sign, okay, to show that's negative. Now, if we plug in 0, 1, what do we get? Well, we have 1 times e to the 0 is 1, plus e to the y, e to the 1 is e, over x e to the y, so x is 0, that's 0, plus e to the x is 1. We have negative e plus 1, that's our slope. Now, if we were to plug this in point slope form, y minus y1, m times x minus x1. Okay, your generic method of finding the tangent line. So y minus y1 equals m times x minus x1. And we get y equals negative e plus 1 x plus 1. And we're done. We just found our tangent line. We just found our tangent line. I think we can do one more. Let's apply what we've learned and sketch a graph. We want to sketch a graph of f of x equals x e to the negative x. Okay? X e to the negative x. Now, first we need to find if there are any zeros. Okay? Now, the equation is conveniently given to us as a product. So you can see that there's a 0 at x equals 0. So let's draw some axes. Okay, so we have some axes, and we know that x equals 0 is a point. Now, we want to find if there are any vertical or horizontal asymptotes. So let's express this as x over e to the x. So we have a quotient, and that helps us better with this step. Now, are there any values of x that make the bottom value 0? Because that indicates a vertical asymptote. Now, that is never true. Okay, e to the x cannot equal 0. So there are no vertical asymptotes. However, are there any horizontal asymptotes? Well, yes, there sure are. Okay, there sure are. Because as x becomes larger and larger and larger, you have the denominator starting to overpower the numerator, okay? You can actually evaluate this limit to be 0, okay? We'll learn how to do that. Oh, oops. We'll evaluate how to do that in a later video, but as x becomes larger, you have an exponential in the denominator. So this becomes the limit as x approaches infinity is 0. So y equals 0. Okay, so just intuitively, you have an exponential function that gets exponentially larger, while you only have a linear function at the top. So it will be 0. So you have a horizontal asymptote. So you know it's going to have to approach 0 in some way. Now, we want to find intervals in which f is increasing or decreasing and find any extrema. Now to do that, we find a derivative. So let's use the product rule since it's a bit easier to work with. So we have f prime g, so f prime is 1, plus g prime, which is negative e to the negative x, times x. Okay, just chain rule. So we have e to the negative x minus x e to the negative x. Or e to the negative x, factor it out, 1 minus x. And with this factored form, you can see that we have a critical point at x equals 1. Let's call this 1. Now, the y-axis. Now, at x equals 1, what do we have? Okay. Now, to the left at 0, you have this is always positive. Okay, an exponential is always positive, no matter what value of x you take. So we only have to look at this expression, which you can easily see is positive when x is less than 1 and negative when x is greater than 1. Okay, so you have a maximum at x equals 1. Okay, and if we were to evaluate this function, you have a max at 1, 1 over e. And there are no minimum values. There's only one critical point. So I would guess 1 over e to be right over here. Okay? Now let's look, okay? Let's look at the second derivative to see if there are any inflection points. F prime prime of x, and let's use this factored form. It's a lot easier. So you have f prime of x. So the derivative of the first function, we apply the product rule again. Times the second function, plus the derivative of the second function, times the first function. So you have negative e to the negative x minus negative e to negative x times 1 minus x minus e to the negative x. And if we factor out negative e to the negative x, you get 1 minus x plus 1. So you get negative e to the negative x times 2 minus x. And you can see that there's a potential point of inflection at x equals 2. Sorry, it's starting to circle around the graph. So the potential point of inflection, x equals 2, we want to check, and this is always negative since you have that negative sign over here. Okay, so this term is always negative. So you could see that for x is less than 2, you have a negative times a positive, so that's always negative. And for x is greater than 2, this quantity will be a negative. So you have two negatives that form positive. So you have a point of inflection at x equals 2. So you have a point of inflection at 2 over e squared, which I believe is even smaller. Okay, and it's concave downward for all values of x less than 2 and concave upward for all the values of x greater than 2. So I think we have enough information so we can actually try to sketch this graph. So it's increasing up to here. So we're going to make it increasing but concave down. So it should be sort of curving down. Okay. So it hits here, but so it's just start decreasing, but still concave downward. So we keep on curving down until it hits here. Then it still decreases, but now it's concave upward. And we see we start to approach 0. Okay, now so you see that the graph of x e to negative x kind of looks like this. So there's a much more variety of problems dealing with the exponential function e to the x, okay? And we're going to study more of these exponential functions in integration next video. Okay, see you soon. And if you have any questions, please comment below. Make sure you like this video and pass it on. Thank you.